So far, we have explained all the essential pieces we need to type math in the Jupyter Notebook's Markdown environment using LaTeX math. So now we want to turn our attention to the coding part that uses sympy in Python to do algebraic operations. First of all, a very frequent operation you will encounter is to take derivatives throughout this course. So how do we do that? Well, we've already seen in our introduction video about using the diff function in sympy to take derivatives. The diff function takes two different arguments or inputs into the function. You need to specify what is the function that you would like to take derivative. For instance, in this case, we want to take derivative of qd. And then you need to specify what is the derivative taken with respect to. And in our case, we take derivative with respect to p. So we need to specify that after the comma. So the comma separates the two inputs in this function. And in Python, it doesn't matter if I add spaces between these inputs, it will be evaluated identically. So I can run this cell, it's going to be minus 20, exactly the same answer we received by calculating it by hand. That's quite reassuring. Sometimes in sympy, it turns out that we don't necessarily have to take derivative this way. Sometimes it's more natural to have an object first, and then we say, well, let's just take derivative of this object with respect to a different variable, which is p. And this kind of way of writing that we put the object that we want to take derivative first in the first place, and then use a dot diff type of operation has a name in Python. This is a general way of using many different functions, and whenever they can be used this way, this diff part is no longer being thought of or called a function, it's being called a method. That's just a technical thing in Python, but you can just think of it as a different way of using a function. Okay, so to take derivative of qd with respect to p, another way to write it is to write qd dot diff. So we're going to take derivative or differentiate this first object, okay? And then we're going to differentiate that with respect to p. That's listed in the parentheses. So now the diff method only takes one input, and that is the variable you want to take derivative with respect to. Now, let me run this cell, and then it's going to give me exactly the same result. So these two methods are both equivalent. Feel free to use either one. All right. Another useful thing in sympy is the use of a particular function called rational. And that function has something to do with the way computers understand numbers. So the idea is that in general, computers store values in a very precise way, but only to a certain level. So for instance, computer doesn't store the whole sequence of pi. So it might store 17 digits after the decimal point, but it never contains the entire sequence unless you explicitly ask it to do that, right? The reason is because if the computer does that for every possible variable you have in a computer for everything, you won't have enough memory to process everything. All right, so the computer always does some kind of approximation. And the issue with that is if I divide 1 by 13 and then store that value in something called x, and then multiply that x by 13, the result is actually not exactly 1. Sometimes the computer will approximate it back to 1, but underneath the computer never really understands it's precisely 1 again, just by dividing and multiplying it by exactly the same value. Usually it is okay, but occasionally it runs into some kind of issues. So sometimes to avoid those kind of potential issues, you will see us use this function here. This is called rational. So the rational function is a function in sympy because we're treating these variables as we would in algebra. So instead of storing 1 divided by 13 as the precise value it's just going to record it as a fraction. So Python never really evaluates that number. So if we multiply that by 13, sympy or Python would understand that 13 and 13 will cancel out, and the result will be exactly 1. This is why you don't see the decimal point. This is not just a matter of displaying differences. It's in fact there are some underlying numerical things going on. So sometimes we feel it might be a little bit safer to use rational, and this is why I usually err on the cautious side and use rational. All right. Another useful thing, in addition to rational and taking derivatives, is we need to replace values frequently. So in the class, we discussed that to get a plottable demand function, we take this QD function up here, and then we'll plug in very specific values for PB, PK, and Y, and then it becomes a single variable expression for the demand curve. So how do we do that? Well, the function to complete that operation in sympy is called subs. It stands for substitution. And it has some very particular kind of syntax. So we just have to follow the way it is defined so that sympy will understand us. All right, essentially what we're trying to do, ignoring all the braces and the scary brackets and all that stuff, we're trying to make a replacement of 3 different objects. We're going to replace PB by the value of 4. Want to replace the value of PK by the value of 10 over 3. In the class we talked about it's 3 1/3, I think. And then want to replace the value of Y by the value of 12.5. Now, in each one of these parentheses, I am just listing the values we want to replace and the values we want to put in or plug in or substitute in. And each one of these objects are separated by commas. Right? Maybe to make this seem a little bit cleaner so you can identify the differences, this is what we're trying to do. I'm just listing these 3 objects that we want to plug in. The parentheses here are a little bit dizzying. The reason is because this is a function on its own, where this is rational number 10 divided by 3, and we're replacing this value into the position of PK. All right. Now comes to the use of substitution. And this is just the way the function is defined in sympy, and there's really, again, not too much reason about why it is the case. So it needs to use parentheses first and then the square brackets, right? So it's a little bit weird, but we'll have to live with it. Now, we're going to replace these 3 objects in QD, and then we're going to put the result into something called demand. And now, on line 4, I'm just trying to call demand and ask sympy to tell me what is demand and see if we actually got the right thing. All right, now let me try to evaluate the cell. What do we got? We got 284 minus 20p. That's exactly the expression we got in class. Voila. Now, with these things in place, we're almost ready to plot a demand curve with the above specific values for PB, PK, and Y. Let's try that. So remember in class we talked about plotting a demand curve will involve inversing the demand function. And the reason is because we want to plot P on the vertical axis and Q on the horizontal axis, whereas when we look at a demand function, it is a function of Q written in expression of P, right? So we need to inverse them. So to do that, we actually need to introduce a new symbol Q here, which we have never defined and used thus far, so that sympy would understand that it is a symbol and should be treated as a symbol. So first of all, decline an additional symbol. Q is symbols Q, just the way we would previously would define these bunch of P, PB, PK, and Ys. Okay, so now I'm going to add another symbol here, which is Q. And now I'm going to try to inverse this particular expression. So how do I inverse this expression? Well, the expression is essentially demand is equal to Q, right? It is Q is equal to 286 minus 20p. So how do we solve this equation? Well, notice that this equation is equivalent to demand minus Q is equal to 0. So now the syntax required by sympy is a little bit weird. It does not recognize the equal sign in there, and it requires you to essentially clear out one side of the equation and then put the other side into the solve function, and then it will implicitly treat this thing to be equal to 0 and try to find the solution to it. So now we're just going to rewrite demand equal to Q, or Q equal to demand, into this form, which is demand minus Q is equal to 0. I'm going to put this part into the solve function as the object we want to solve. And then in addition to that, we need to tell sympy what is the variable we want to find. And in this expression, we're trying to solve for p because we're trying to rewrite the demand function, which is q equal to 286 minus 20p, in terms of q, right? So we want to write p as an expression of q. And that's what we'll try to do. Now, let's look at what we have here. Line 7 here, I am just calling dplot again, so that Python returns what dplot is to me, so we can check the answer. Oh, all right, now let me run this cell. And here we go. We found the solution. This is 14.3 minus q over 20. That's exactly the expression we have in the slides. Now, notice that in this solution, the answer is wrapped around in square brackets. Well, what does that mean? This is in fact something related to Python in general. Square brackets here represents something called list in Python. And this has something to do with the way Python stores data. For a computer language, it usually stores some kind of value, in particular when you require the computer to carry out some explicit calculations for us. And usually when we use Python, we would require Python to store a lot of things we need to use. For instance, we store the particular symbols of q and p and pk, etc., etc. We solve a particular equation and the result is stored in Python in some way. In general, let's say that you want to store the temperature of Lewis domain today for each hour during the day, then you need to store these data in the computer. And then you will be able to access them later on. So in order to access them later on, you usually store it into something that has a particular name, so you can refer to it, right? For instance, here we have this particular solution. We're going to call it dplot so that we can plot the demand curve later on. So it's stored in this thing, and now if we refer to dplot, Python recognizes that label, and then it's going to kick this value that is stored back to us. All right, now in general, Python can store things one by one that says, okay, A is 1, B is 2, C is 3, etc., etc. Sometimes it is much more convenient to store a bunch of values in groups. For instance, we would have a drawer where we can put in a screwdriver, a thermometer, a napkin, etc., etc. Of course, it's not a very organized drawer, but it's a drawer nonetheless. So this kind of thing is called a list in Python. So for instance, let's create a list L. And to tell Python this is a list of things, we're going to use square brackets. And let's say in this L, this list or drawer, think of it that way, we can have several things or several objects, several elements or several items that are contained in there. The first item can be 1, the second item can be 2, the third item can be 90, and then the fourth item can be test, and let's say the fifth item can be Bates. All right, and this is totally fine. Let's run the cell, so it's being evaluated, but it doesn't generate anything. Now let's try to create a cell below, which is again in code, and let's just ask Python what is L. And now Python is going to tell us L is in fact a list. It has these 5 things in it. So now you're going to say, well, what if I only want to access the second thing in this list? Now this has something to do with accessing an element or an item in the list by their index. So what do we mean by this? This list here has 5 items, and they're each indexed in a particular way. For instance, they're ordered like this because we put them into it like this. Python doesn't just store these values we put in, and when it's put in these values, it understands that they're ordered in a particular way. For instance, we understand intuitively that the first element is 1, second element is 2, third element is 90, etc., etc. So Python stores these things and creates an implicit index to go with them. The tradition in Python is the first element has an index of 0. The second element has an index of 1, and 2, and 3, and 4, etc., etc. So to access the first element in L, what do? We need to put a square bracket behind L and then put 0. This will give us the first element of L, which is 1. Well, what if we want to access the second element? Well, we put in index of not 2, but 1. Now it returns the second element, which is 2 here. What about the third element? Well, we use index of 2. What about the fourth one? Well, 3. That'll give us that text, which is test here. Well, the reason we want to bring about the notion of list items and index is because the solution here we obtained is contained in a list. Now let me remove these things for now because we don't need them anymore. The idea of sympy is that some equations might not have a unique solution. So for instance, if you solve a quadratic equation, you're going to likely have two solutions. And when you have two solutions, what does it do? Well, it's going to save both of those solutions into a list. There is going to be a first solution and a second solution. Of course, they're not ordered in any particular way, but they're going to be stored as such. Okay. In this case, we have a linear equation. When you solve the linear equation for the unknown, you will have a unique solution, but it is still stored in the format of a list. And the issue with the list is that whenever we refer to dplot, it's not going to give us the element inside. It's going to only refer to this box, although the box only has one thing inside. So in fact, when we want to use the content or the item inside the solution, we need to refer to the item inside. In this case, it only has one item inside, so I'm going to refer to its index of this only item. Because it's the first item, the index for it is 0. So if we just type dplot square bracket 0, now you can see what's being returned does not have the square brackets around it anymore. And this is because it is the element inside and just the mathematical expression for the solution as opposed to a list of all possible solutions. Now we're ready to move on and look at the next cell. So in this cell, essentially what we've done is I have rewritten the solve command again. We're solving the linear equation for p, and that's exactly what we did here. But instead of doing it in 2 steps where I solve it, save it to dplot, and then retrieve the first element in dplot, I can directly solve and then take out the first element in the solution and store it in something called d inverse simple. Now let's try this. You can see that it's exactly the same result. And this item is exactly the mathematical expression for our demand curve, where we have Q is equal to 14.3 minus Q over 20. And now we're ready to plot it. Right? To plot the demand function, we need to use a plot function. And it takes some inputs. And let me break that down for you. In this case, at least we need to specify what is the object we want to plot. Well, we want to plot the inverse simple, which is this particular expression. Of course, you can also select to plot d plot square 0. That will give you the same thing. To plot this function, we want to restrict the range in the q-axis or the horizontal axis. We only want to plot the function between 0 and 286. Well, 286, as we see in class, is the horizontal axis of this linear demand curve. And now the third and the fourth inputs to this function are just the labels for the x-axis and the y-axis, because we're plotting q on the x-axis or the horizontal axis and p on the vertical axis or the y-axis. This is how we're going to write it. In other words, we're telling Python that the x-axis is q, the vertical axis is going to be labeled as p. Notice how we have dollar signs in them. And this is LaTeX again. So now when Python reads it and makes a plot, it recognizes that the labels should be processed through LaTeX so they look more mathematical. And now let's run the cell. Sometimes the first time you run it, the output won't show. In that case, just run it again, and you should be able to see it. And voila, we have our demand function. Q on the horizontal axis, P on the vertical axis. The horizontal intercept is 286. The y-intercept is at 14.3. Exactly the way we want them to be. All this work might seem like a lot, but it turns out that if we keep going on the course, you will realize that the pieces are being used most frequently and repeatedly are essentially taking derivatives, making substitutions, and make some plots. So just by knowing these few functions, it gets us quite a bit of mileage going forward, and we'll see how they're being used from case to case. And I'm sure that in a couple of weeks, through plenty of exercises, as long as you put in the hours and effort, everyone can do this. So don't freak out. Take your time, be patient with yourself and with the process. Make sure you discuss with your friends and make sure you talk to TAs and me when you have questions.